Hi guys, this is Mrs. Foy, and this is a screencast about how to calculate empirical and molecular formulas. This is sometimes difficult for students, and so you may need to watch this video a couple of times to get the steps, and then you can practice. So the first thing that we need to go over is that there is a difference between the empirical formula of a compound and the molecular formula. The molecular formula and the empirical formula can be the same, but sometimes they're different. The empirical formula is kind of the generic formula. It's the base formula that tells you the ratio of the different elements in the compound, and the molecular formula gives you the actual number of the different elements in the compound. So for example, here I've got an empirical formula of H2O and the molecular formula is the same. But here the empirical formula is P2O5 and the molecular formula is actually P4O10. Notice that the molecular formula follows the same ratios of the subscripts over here, but they're telling you that it is exactly 4 phosphoruses, 410 oxygens. Here I've got C5H12O as the empirical formula, and the molecular formula is the same. But here I have C2H6O as my empirical formula, and over here the molecular formula is still following this generic empirical formula ratios. It's saying I have to have 2 times as many carbons, 6 times as many hydrogens, and 1 oxygen for each of those. So C6H18O3 is following the generic empirical formula ratios there. So what you have to do in empirical and molecular formulas is you have to calculate the empirical formula first, and then you just have one other step that you have to do to calculate the molecular formula. Remember, sometimes they're the same, and sometimes they're going to be some whole number multiple different, the molecular formula from the empirical. So let's get started. So guys, there's 4 different steps for calculating the empirical formula. The first thing is that sometimes you're given the percent composition of each of the elements in the compound, and so if that happens, you just assume that you have 100 grams so that the percent becomes grams. The second step is that you have to convert the grams to moles, so you have to figure out the molar mass and convert to moles. The third step is that you take the smallest number of moles and then you divide all of the moles by the smallest mole to get the mole ratios. And then if you don't get a whole number in that step 3, then you have to double or triple to make those integers a whole number. So let's get started. Here's a practice problem. Methyl acetate is a solvent used in some paints. Determine the empirical formula for this compound if it is found to be, and here I can see that they're giving me the percent composition of the different elements in the compound methyl acetate. So 48.64% carbon, 8.16% hydrogen, and 43.20% oxygen. So to get rid of those percents and get to grams, all I have to do is just assume 100 grams. And so the 48.64% carbon becomes 48.64 grams. And the 18.16% becomes 8.16 grams, and the 43.20% becomes 43.20 grams. So that's step 1. Step 2 is that now I'm going to use the molar mass of each of these elements and convert to moles. So here is the molar mass of carbon, 12.01 grams. I got that from the periodic table. Here is the molar mass of hydrogen, and here is the molar mass of oxygen. And I just set up my conversions so that the grams go on the bottom and the moles go on the top. So when I multiply times the masses that were given to me in the problem, my grams cancel and I get to moles. So I get 4.05 moles of carbon, 8.08 moles of hydrogen, and 2.70 moles of oxygen. So now to get the ratios, what I'm going to do is I'm going to divide by the smallest mole, and the smallest mole in this case is the moles of oxygen. So everybody gets divided by 2.70 moles So I'm going to take the moles of carbon divided by 2.7, the moles of hydrogen divided by 2.7, and the moles of oxygen divided by 2.7. So I get 1 mole of oxygen. I get 2.99, and I'm allowed to round that to 3, but I get 1.5 moles of carbon. And unfortunately, I cannot have a subscript in an empirical formula be a number that's not a whole number. So I'm going to have to do that fourth step, and that fourth step is that I've got to get to a whole number. So because of that troublesome carbon at 1.5 moles, I have to multiply everybody times 2 to get a whole number. So 1.5 times 2, 3 moles of hydrogen times 2, and 1 mole of oxygen times 2 gives me 3 moles of carbon for every 6 moles of hydrogen for every 2 moles of oxygen. And that is my empirical formula. So I get C3H6O2. And that is the empirical formula for methyl acetate. So now let's do another problem. A compound was analyzed and found to contain 13.5 grams of calcium, 10.8 grams of oxygen, and 0.675 grams of hydrogen. What is the empirical formula? Well, in this particular case, they gave me the grams and not the percent. So I can skip step 1 and go straight to step 2. So I'm given the different masses, and now I'm going to use the molar mass from the periodic table, and I'm going to convert to moles. And I am also doing step 3 here by dividing by the smallest mole. So I get so many moles of carbon, so many moles of hydrogen, so many moles of nitrogen, and so many moles of oxygen. And I can see that 0.68 is the smallest number of moles for this problem. So everybody gets divided by 0.68, and I get 7 moles of carbon, 8.97, so that's close enough. I can round that to 9 moles of hydrogen, 1 mole of nitrogen, and drats, 2.5 moles of oxygen. That's not a whole number. It's not close enough to be a whole number, and so I'm going to have to multiply everybody times a whole number to I'm going to have to multiply everybody times the number to get a whole number for my ratios. So because of that oxygen being 2.5, I need to multiply him times 2 to get 5, and that means I have to do the same for the moles of nitrogen, for the moles of hydrogen, and for the moles of carbon. And so I get C14H18N2O5, and that is my empirical formula. So what about a molecular formula? How do you do that? Well, you have to calculate the empirical formula first, and then you also have to be given the molecular formula mass to be able to do the problem. So what you do is you take the molecular formula mass and you divide it by the empirical formula mass that you calculate from the empirical formula. So here's an example. Caffeine has an empirical formula of C4H5N2O. So in this case, they just gave me the empirical formula. What is the molecular formula if the empirical formula weight of caffeine is 194.19? So they have to give you this, guys. They have to give you the molecular formula weight in the problem. And then the empirical formula weight, I can calculate if I have the empirical formula. So I just take the mass of carbon times 4, the mass of hydrogen times 5, the mass of nitrogen times 2, plus the mass of oxygen, and I add that all up, and I get an empirical formula weight of 97.11. So I take the molecular formula weight divided by the empirical formula weight, and I get 1.999. So that's very close to 2. So I take the empirical formula that they gave me in the problem, or a lot of times you have to calculate that, times 2, because that was the whole number that I got when I divided the molecular formula weight divided by the empirical formula weight in the last step. And so my molecular formula is N4O2. Now, if you're lucky enough to get 1, if you actually have the empirical formula weight being the same weight as the molecular formula, then it's one of those cases that the empirical formula and the molecular formula are the same. So this is one of those situations, guys, where you definitely have to practice problems. So watch this screencast one more time if it's helpful, and then practice problems on your own. See you in class.